Hello everyone, welcome to my presentation. I'm presenting to you our framework. Our paper name is Norma, a framework to find threshold association between continuous variables using pointwise function. I'm MD Mahin, and this work is done with me and Dr. Christoph I, and it is from the Department of Computer Science of University of Houston. So this is how my presentation is organized. At first, I'm going to present our scope of our research. Then I'm going to introduce the pointwise function. Then I'm going to introduce association analysis, research gap in the literature, and our contributions. Then I'm going to introduce our framework Norma, which will then include CVT patterns and interestingness measure. Then I will present our case study we have done. Then I will introduce another contribution of our work as a grid-based hotspot discovery algorithm. And finally, I will conclude with the conclusion and the broader impact. So what is the scope of our research? Actually, we are interested in finding association among continuous variable, more precisely special continuous variable. And we are aiming to find how strongly values above certain thresholds from different special continuous variables are related. For example, we are trying to answer the question that what is the strength of values above two thresholds from two special continuous variables. For example, let's say with COVID-19 infection rate and the infection rate above 0.15, 15%, or environmental variable pollution parameter PM25 above 8, how strongly these two are related. Or we can also ask a question like COVID-19 infection rate above 40% or 0.4, medium income above 70,000, and poverty rate above 25%, how strongly they are related. So this framework is actually based on a pointwise function, and it operates on pointwise functions. And we try to measure actually what is the actually how strongly values of different pointwise functions are related. Pointwise function thresholds are strongly related. For example, if we read the previous example, we see like pointwise function from COVID-19 infection rate above 0.15 and pointwise function from PM25 above 8, how strongly they are related. Or pointwise function from COVID-19 infection rate 40%, or pointwise function related to median income and value 70,000, and pointwise function from poverty rate and value threshold 25, how strongly they are related. So this is actually for one threshold. We also aim to calculate such associations for all possible thresholds related to each function. Then our intuition of this research is very simple. When there will be a strong association, we expect hotspots from different pointwise functions will appear on the similar locations. So actually, what are these pointwise functions? Let's say a pointwise function will take input as a location and return corresponding value for that variable. For example, let's say we have pointwise function related to PM25, and we give it input a location which is Santa Fe Plaza. It may invoke different functions, special functions like density function, interpolation function, or polygonal pointwise function. And this function will go through that location and somehow calculate what is the value of PM 2.5 on that location, and will return a value like, for example, 3 in Santa Fe Plaza. Now, what happens is when we apply pointwise function, the analysts don't have to bother about the underlying heterogeneity of the data and perform the analysis using the function. So it becomes a function-based framework, not apart from the heterogeneity of whatever data is. So our framework belongs to the association analysis family. And what are the association analysis? Normally, association analysis, if we have a data set D and we are interested to for a possible set of pattern P from the data set, and we are interested on certain association A, and we have a certain interestingness measure I for that association, and we want to say like for that interestingness measure if it is above certain threshold theta. Very simple example is like correlation. For example, we have a data set D with PM25 concentration and bronchial asthma rate, and we want to find what the if the pattern correlation of this will be interesting if it is has above 0.75 positively or negatively. So absolutely, our interestingness measure becomes the absolute value of correlation of PM25 or bronchial asthma. So if we discuss about sample association measure from the literature, we can discuss about bivariate Morani because special associations for multivariate analysis is very scarce. This is one example that is often used for two variable association. In bivariate analysis, suppose we have two variable continuous variable A and B. A and B are first divided into high-low patterns. For example, A is divided into A high and A low, B is divided into B high and B low. We can mark each pattern with respective color. A high is red, A low is purple, B high is green, and B low is blue. Now, what the bivariate model tries to find is if high values from one variable is surrounded by high values from another variable, and low values from one variable is surrounded by low values from another variable. In such case, it is very strongly related. And if opposite happens, like high values from one variable is surrounded by low values from another variable, the strength of the association is low, very low. So actually what it's doing is like it tries to find like association between high and low values from one variable and a special lag of another variable. A special lag means the how other variables are values of other variables surrounding this particular values from another variable, not directly how they are associated. Now, what are the problem in this literature? Do they measure any continuous variable association? No, actually. They first, you can see first, they divide each variable into high and low. So there is no continuous association. There is categorical association. Is it a multivariate association? Actually, no, because bivariate Morani, even though it is bivariate, it is actually developed as an univariate measure. In univariate measure, what happens is like it's developed to find if high values from one variable is surrounded by high values of that one each variable, like values of one variable is surrounded by a special lag of the same variable. Now, as there is no multivariate association analysis, special association analysis available, people started circumvented it and like started developing using replaced a special lag with values of another variable to find bivariate analysis. Now, so can we then extend it for three variables? No, like this is the limit. For bivariate model, it is only extended for expandable for the two variables only. So is there any agreement value? Like how can I say like if the values above this, how these values are strongly agreed upon, like how they agree? We can't say anything about that. There is no notion of agreement, no notion of like particular association. Just it's a kind of a statistical measure to find like how they are associated statistically. So how can we say like how the different values, subset of values are really like associated in this area? It's not possible because now at the beginning of the association, we are dividing each value into high and low using whole domain of each variable. So we can't say how particular subset are associated in this region. So it's not possible. So what actually research gaps and what are the contribution of our work? Actually, in a special domain, there are not much work with multivariate association. Correlation is an example, bivariate model is an example, but we are actually aiming, can we extend the capability of this type of research? Measures such as correlation of bivariate analysis finds association among only two continuous variables, but we are introducing thresholds to find different subset of values, like correlation finds to these measures generally use full domain of values, where we are trying to find the subset of values and find the association among that subset of values. And that is why we make the following contributions. We propose a completely novel pattern, continuous variable threshold patterns, because as there is no pattern available. Then we find develop interestingness measures to find association among within that pattern, and for different thresholds. And we also propose threshold independent interestingness measure using this proposed pattern, and perform the case study to show the effectiveness of our measure. So actually, special next we define like this pattern, special continuous variable threshold pattern mining. So our intuition is very simple. Our Norma framework is developed on a very simple intuition. Hotspots from 2.0s function will appear similar location, and they will then they will have very strong association. So we try to find agreement among the hotspot or regions about respective thresholds from pointwise function. What do we do? This is why we develop this interesting numinous measure I, which take input a pattern. This pattern has like a variable and a threshold, two variable and threshold pairs, VT and V dot T dot, and it measures the agreement between the hotspots. How it measures it? For example, it first for our edge function takes the pointwise function related to our first variable V, and takes the threshold T and find the all hotspots where all values are above this threshold T. This is a sample threshold for V, hotspots for V. Then same we do for the second variable V dot, and we find the hotspot out of the pointwise function above for related to V dot and above T dot. Then we find the union and intersection, like what are the union hotspot of these two regions. This is the red and what are the intersection. For example, this red region is intersection, and the whole red and blue region is the union. Then what we find agreement, and which is intersection by union. And for example, if we find the union by intersection is 0.30, then we say like there is a 30% agreement. Now, this is for one thresholds. What happens? We measure it for all thresholds, like for all possible thresholds. This is one example from COVID-19 infection rate thresholds and bachelor degree rate thresholds. And we can say like this is not a the interesting measure is not a simple curve. There are different high and low curve within that like same for different varying thresholds. Then we study the behavior, and we do it for like 15 into 15 thresholds for two variables. One is COVID-19 infection rate and bachelor degree rate, and COVID-19 infection and median income thresholds. What we found that mostly like in lower thresholds we find global maximum, but sometimes they can appear as trivial pattern. What are the trivial pattern? Like when the thresholds are low, hotspots cover whole observation area, and we find very high interestingness. So we measure we restrict hotspot must be cover below a certain limit of threshold. Then we additionally find there are other maxima in the middle of the hotspot interestingness, and we call them local maxima. But problem is sometimes we find low support patterns, like where hotspots there are like random hotspots coverage occurring together, and there are very high interestingness, so support is very low. So to like prevent it, we say like hotspot must cover a particular above certain thresholds. So can we reduce the complexity of this algorithm? Yes, we can replace the hotspot generation by instance counting. For example, for intersection, we count like total thresholds above T dot in certain regions, and for union hotspot, we count like total points and above threshold TNT dot, and then we measure it. What is the problem? So this is one example without approximation, and another is with approximation left and right. And we can say like we may lose some information like local maxima for with approximation, which you can find only with the hotspot generation. And how we can like find even if we want to find like a variable pair is how a strong have showing is a strong relation, how we can find it without considering the thresholds. There is one is AUC. So AUC is what is the for a variable pair, what is the average area under the curve of the interestingness measure. So it's measure the average interestingness for all possible thresholds, and like this is the average for this special variable pair. So we performed a case study. Our case study collects data from COVID-19 data repository and New York Times COVID-19 data repository, and our data has 20 county level variable for the whole continuous use, and we analyzed a total of 235,000 patterns with from 190 variables from these 20 variables. And we compared it against Pearson correlation and bivariate Morani, and these are our variables. We find out that this is some sample results from AOC, where you can see that population density and household density has very high Pearson correlation, high bivariate Morani, also high AOC. But trade employee rate and household density, also population density, average precipitation does has very weak correlation, very weak bivariate Morani, also very weak AOC. So what we can see, like AOC shows almost similar relation like Pearson correlation and bivariate Morani. Like where they are high, the AOC also high, where they are low, AOC also low. But when even there is no correlation or association for Pearson correlation or bivariate Morani, because like something similar to zero in this both cases, there it means there is no relation. Our AOC can find like there is at least 10% to 14% on average agrees different for different thresholds in these two variables. Now, another the most strongest point of our method is we can go through these individual thresholds and check how much they agree, which is not possible for these measures. So we can select these thresholds agree this person. One time, like for fear, there is might be some values agree 50% area, some value agree 40% area, but for Pearson correlation on bivariate Morani, it's not possible to see how subset of the values agrees. So actually our measures gives more detailed overview how the actually overall association is which traditional measures be missing. We also measure similarity among these measures. So what we did is for 190 pairs, we ranked each pair like based on the value from positive to negative. For example, population density, household density ranked 190 for all measures, but trade employee rate and household density ranked differently for all measures. And we found rank measures rank correlation, and we found that like their correlation is very high, 0.7473. So we say like they have similar ranking, almost similar ranking, but there is no perfect one. There is slight indicators of some dissimilarity. As the measures are different, it is expected. So we also propose a hotspot discovery framework, discovery algorithm, which is a novel contribution of our work. Our hotspot discovery algorithm, actually a grid-based hotspot discovery algorithm, where we employ grid over the observation area, and we find like grid points are above or below the thresholds. For example, red points are above the thresholds, blue points are below the thresholds, and we measure and each 2 points actually has certain distance between the neighbors, DR etc. Now we find like all connected points. Now connected points are where or actually if two neighbors are above threshold T. Now as if we find hotspot this shape, it can be very irregular and spaghetti-like, and sometimes would it be impossible to find agreement. So what we do is we find like where hotspots as street hotspots where all cells from certain area are above the thresholds. So this way actually hotspot generated returns all these cells as a single hotspot. Now it has way low complexity because like we are using sampling to generate hotspots now, so we don't have to count amount of time or measure density. And also the polygon generation is very simple, just return the grid point, union of the grid point. So it's way simple to generate and has way less complexity and than any traditional measures or traditional clustering algorithm. So what are the conclusion and broader impact of our work? Actually, we are proposing a pointwise function-based association analysis framework, and that finds reveal unique patterns and interesting mismeasure. And it is a very novel approach to calculate a special multivariate analysis for continuous variables. And actually it provides insight that similar to traditional measures, but its scope is way larger and broader impact is for example, our method can be used where all special continuous variable exist, like public health. We can detect like if high cancer thresholds occur associated strongly with high PM2.5 thresholds, or like environmental, like if low temperature is related to humidity, high low different humidity dynamics thresholds, or urban planning or policymaking. For example, if high crime rate is associated with low security infrastructure density in certain regions. So this is all our framework. Thank you for listening to it, and best of luck.